So welcome back everyone for the second lecture. So please type your roll number in full at the chat box. That will be automatically recorded and will be considered as your attendance. So let me start immediately at 10 a.m. because we have only 40 minutes slot. We will not be able to cover anything much unless I start exactly at 10 a.m. So as I was discussing, please pay attention. You can type your attendance also. And at the same time, everyone, you can mute your microphone. I think everyone is muted. Uh, so what we are discussing here is that we are now looking at three types of material. The first one, the leftmost, as we can see here, it is called insulator. Insulator is a very layman explanation of an insulator is that uh, a material which cannot conduct electricity. So from this energy band diagram, you can see that in insulators, we don't have any free electrons. No free electrons. We don't have no free electrons, right? No free electrons. So we don't have any material, any charge carrier, we should say. Okay, free electrons, as you see, as it moves from one place to another place, it can conduct electricity. Then we call it a charge carrier. So we don't have any charge carrier that will contribute to electricity here in an insulator. Why are we not having any charge carrier? The reason here, as we discuss here, is that when the atoms constituting in an insulator form the solids, all the valence electrons participate in the valence band, or all the valence electrons participate in the chemical bonding. All the outermost electrons participate in the chemical bonding. So the electrons in the inner cell of an isolated atom uh, is within that atom itself. It cannot participate in any chemical bonding, nor it cannot contribute to any free electrons because they are well deep within the atoms, right? They are well deep within the atoms, so they cannot contribute for any electrical property of the material. So what can contribute for electrical property of the material is always those electrons in the outermost cell called the valence electrons. So in an insulator, all the valence electrons participate in a chemical bonding, and the chemical bonding is so strong that you cannot easily detach electrons from the chemical bonding. You cannot easily detach electrons from the chemical bonding between two atoms here. So in order to set this electron, which participate in the chemical bonding between atom 1 and atom 2 here, you need a very large amount of energy to detach these electrons. So that energy required to detach these electrons or to set these electrons which already participate in a chemical bonding as a free electron is greater than 5 electron volt. So when the energy required to detach these electrons, which is already in the chemical bonding, is greater than 5 electron volt, we can see from the energy band concept that in order for the electrons to lift them from the valence band to the conduction band to become free electron, we need more than 5 electron volt amount of energy. So therefore, under normal circumstances, that is at room temperature, the thermal kinetic energy which is associated with any gas molecules or any particular atom or electrons, any entity, we can write it as 3 upon 2 kT averagely. So the thermal energy cannot detach these electrons at room temperature, and therefore at room temperature, at normal circumstances, an insulator cannot have any electrons which are free. So therefore the insulators cannot conduct electricity. They don't have any free charge carrier like electron here. But however, in the case of a conductor which is on the rightmost here, uh, those electrons, you see that there are K cell, L cell, and all. So the outermost cell will consist of electrons which are known as the valence electrons. So within this, there will be some inner cells and all, depending on the size of the atom or the atomic number also, right? So depending on that, so all these inner electrons, they cannot contribute to any electrical property here. They will constitute the the potential field within the atom only, but they cannot contribute to any other external property here. So in a conductor, when the atoms constituting the conductor form a solids, some of these electrons, they will be participating in a chemical bonding. Those electrons participating in a chemical bonding, they will lie in the valence band, right? They will lie in the valence band, but there are some electrons which are not participating in the chemical bonding, and those electrons which are free to move, which are not bound to any particular chemical bonding, they will lie in what is called the conduction band here. So in conductors, there is no energy gap between the valence band and the conduction band here. And some of the electrons, they will be free electrons. Some of the electrons, they will be in the chemical bonding. They will be in the bound. They will be called bound electrons in the valence band. So already in conductors, we have large quantity of free electrons which can easily move under the action of electric field or thermal energy also. If you have a thermal energy that is above absolute 0 Kelvin, say 0 Kelvin, you know that in the absolute zero, everything freezes. Like these electrons and all, even though they are free electrons, they will freeze at 0 Kelvin. Everything freezes at 0 Kelvin. But above 0 Kelvin, there is always 3 upon 2 kT thermal energy associated with it. So because of the thermal energy associated above 0 Kelvin and also at room temperature, all these free electrons, they will have a random thermal motion. They will have a random thermal motion. They will have this much amount of average kinetic energy, and they will move in one particular direction and collide with another electrons or another atom, and then they will alter their direction. So they cannot remain stationary above 0 Kelvin because of this average thermal kinetic energy. They will randomly move. But the random motion of those electrons, they cannot contribute to net transfer of charge. So like for example, in this particular conductor, let's say we have this many number of free electrons. Because of the random thermal motion, some electrons will move in this direction, some electrons move in this direction, some electrons move in this direction, and even some electrons will move in this direction. Like that, upside, any direction, random motion will occur among the free electrons. And there cannot be any net transfer of charges from left side to right side or right side to left side. No net transfer of charge. Okay, under thermal energy, no net transfer of charge. So if there is no net transfer of charge, we can see that there is no electricity, no electrical conduction. Okay, so under room temperature, without the application of any external field, these free electrons can move randomly, but they cannot contribute to electricity. So the reason is that the random motion due to this thermal energy, uh, it takes place in every direction. So you cannot have any net transfer of charge. Therefore, no electrical conduction here. Right. Now, but we know that in conductors, if you apply a potential, if you connect, like let's say this is a conductor, if you connect a battery like this, positive, negative, if you connect a battery like this, the electrons will move according to the direction of application of this potential here. So if you have large number of electrons within a conductor here, if you connect it like this, these electrons will move towards the positive terminal of the battery. So therefore, it will result in net transfer of charge from right to left. Then there will be a resultant current from left to right, because the electron motion here contributes to a current. The electron being a negative charge, the direction of current is conventional current is always opposite to the direction of motion of negative charge. Okay, so here in this case, if you have a battery connected like this, the electrons move from right to left, and then current will flow from left to right. because of the like the negative charge property of an electron. Now, the third material that we will be focusing on in our today's lecture as well as the consecutive lecture is semiconductor. So in semiconductor here, again, similar to valence band, under normal circumstances, all the valence electrons, they will form a chemical bonding. All the valence electrons in a semiconductor, they form a chemical bonding. So it's like this. Valence electrons, they form a chemical bonding, uh, just like the one shown here. So this is a silicon or germanium crystal group 4 element. In group 4 element, we have 4 valence electrons, right? 4 valence electrons. So this is, let's say, an atom, group 4 atom, or let's say this is a group 4 atom. This atom will contribute to chemical bonding uh, by covalent bonding here with neighboring atom, and this will contribute to chemical bonding by covalent bonding. 1, 2, 3, 4. So it has 4 electrons here. All the 4 valence electrons, they will contribute to chemical bonding with the neighboring atom. So ideally, all these 4 valence electrons, as they contribute to chemical bonding with the 4 neighboring atoms, covalent bonding with the 4 neighboring atoms, they will lie in what is called the valence band here. So the electrons, the valence electrons contributing to chemical bonding or participating in a chemical bonding, they will lie in what is called valence band here. Okay, all of them will lie in the valence band there. But the difference between semiconductor and insulator here is that the energy required to detach this electron, the energy required to detach this electron uh, to become a free electron is quite low. The energy required to detach this electron to become a free electron is quite low. Like, for example, at this point here, this is also another location for chemical bonding. So easily at room temperature, that is 3 upon 2 kT energy, some of these electrons can detach. Not all of them, not many of them, but because of the thermal vibration, because of this average kinetic energy, all these atoms, they cannot remain stationary because of this average kinetic energy. All these participating atoms like these atoms, all these atoms, they will vibrate left, right, top, right, like that. They will vibrate randomly. So as they vibrate randomly at room temperature, some of the electrons which are participating in the chemical bonding, they will get detached. So when they get detached, they become a free electron. So this particular electron, which is detached from this chemical bonding, become a free electron. So in energy band concept, we can say that this electron, which was earlier in the valence band or which was contributing or participating in a chemical bonding, get detached and become a free electron. So when they become a free electron, the energy state is known as conduction band here. The energy band in which those free electrons are moving around is known as conduction band. Right. So the energy band in which those detached electrons, those free electrons are moving around is known as conduction band energy. Conduction band energy. Right. So as they detach here, as you can see, they will leave a vacancy. They will leave a vacancy called hole. They will leave a vacancy called hole. That vacancy is called hole. So by jumping to the conduction band here, they create a vacancy here. All right. So in semiconductors, now we see that in order to have free electrons, there is always an associated vacancy called hole. So this is electron, this is called hole. This process is called electron hole pair formation. So when due to the thermal energy, when you dislodge or when you detach electrons from the chemical bonding, they result in a free electron, and simultaneously they create what is known as a hole or a vacancy there. That hole also can contribute to electricity, which I will discuss. So because of that, in semiconductors, we now have two types of charge carriers. The first charge carrier again is called free electrons, which can easily move within the solid, that is within the conduction band. And another charge carrier is called hole, which is simply a vacancy created by the dislodging of an electron. So that hole also can result in transfer of charge. Hole also can result in transfer of charge. So therefore, we have two types of charge carrier. Two types of charge carrier. Okay, two types of charge carriers. Now you can see the difference here. In insulator, there is no charge carrier. We don't have anything at all, right? Because of this high energy, large quantity of energy to dislodge an electron from the chemical bonding. We cannot have any charge carrier. We cannot have anything that can contribute to electrical current. And however, in conductors, as I said here before, there are always plenty of free electrons because not all the valence electrons contribute to chemical bonding. So the valence electrons contributing to chemical bonding, they lie in what is called the valence band, but those which are not contributing to the chemical bonding become free electrons. They lie in what is called the conduction band here. And these free electrons can contribute to electricity. They can contribute to electricity. So we have only one type of charge carrier in a conductor called free electrons. Only one type of charge carrier in a conductor called free electrons. However, in a semiconductor, we can see that we can have two types of charge carrier, free electrons as well as holes. All right, free electrons as well as holes. Remember that. Now, let us see. Now, let us consider that this is a silicon semiconductor. So in this silicon semiconductor, we apply an external battery. That is, this side is positive, this side is negative. So you see that this is a symbol for DC battery. This is a DC battery, direct current battery, right? So one side is positive terminal, one side is negative terminal. So this is supply you're connecting. So you're applying a positive potential here, applying negative potential here. And as I already said, once you created a free electrons, those free electrons will move randomly due to the thermal energy 3 upon 2 kT. They will move. They will have a random kinetic energy, but the random kinetic energy again cannot contribute to any electrical conduction because there cannot be any net transfer of charge. But once you apply a DC battery like this, you see that these free electrons, under the action of DC battery, that is the negative potential here, these free electrons like this, they will have a net movement from right to left. Free electrons will have a net movement from right to left. Right. Free electrons, they will have a net movement from right to left. These free electrons, because the direction of this, the action of this potential field or the electric field applied in this semiconductor will drive them, and they will move to it what is called drift velocity. They will move to it what is called drift velocity. They will drift under the action of this external potential or the external electric field. They will drift from right to left. And at the same time, let's say this is a hole, say electron hole pair formation. So if we dislodge electron from here, they will become a free electron and they will leave behind a vacancy called hole. All right. Now let's say initially this electron was this chemical bonding was occupied by one electron here. Now once you apply a positive potential here, positive field here, and negative field on this side, this electron in a neighboring atom, which is in the chemical bonding, they will be pulled towards this vacancy. They will tend to move towards this vacancy. So the electron will jump from this place to this place, and they will occupy this vacancy easily. And by occupying this vacancy, the electron which was earlier here, it will leave behind another vacancy. And once there is a vacancy in the neighboring atom here, the electron which was already participating in the chemical bonding here, it will find a vacancy here. And also under the action of this external field, this electron will tend to move towards the left side again. And this electron also will tend to jump to that vacancy, and they will occupy this vacancy, and they will result in another vacancy creation here. And similarly, once there is a vacancy in the vicinity here, the electron which was earlier here, under the action of this external electric field, they will jump to this particular vacancy and resulting in the creation of a vacancy here. And similarly here, the electron here, which was here, will find a vacancy in its vicinity, and they will tend to jump to that vacancy because of this external electric field, the negative potential applied here, and it will occupy this position and it will create another vacancy here. And similarly, the another electron will be supplied by this external battery. That electron supplied by the external battery will occupy this location, and then it will result in electron motion from this to this, electron motion from this to this. So what I'm trying to convince you here is that even though a vacancy or a hole that is not in itself a charged particle or a free charge particle at all, but once you create a vacancy in the chemical bonding, it will result in net transfer of charge. How is that? Here you see that there is a vacancy here. Because of this vacancy, electronic charge from this place to this was moved to this, and similarly the electronic charge from this to this was moved to this. Electron from this to this will move to this, the electron from this to this will move to this, and electron will be supplied to occupy this place. So as a whole, whenever we have a vacancy in the chemical bonding in a semiconductor, you can see that there is a transfer of charge from this to this. There is transfer of electron from this to this, right? So even though the movement of hole is from left to right, see, this is hole. Whole movement, as you see, it started from here. Whole started moving from this to this, this to this, and this to this, and subsequently it up to this. So the movement of whole is from left to right, but it results in net transfer of charge from right to left. So this movement of whole, as you can see, it can also contribute to what is known as electricity, because there is a net transfer of charge associated with the movement of hole here. Okay, so please try to picture what I'm trying to convince you here. So we can see that in a semiconductor we can have electrical current due to movement of electrons, free electrons, under the action of external electric field, and also electrical current due to movement of holes under the action of external field. So we have electron current as well as hole current. Electron current, we call it, as well as hole current. Two types of current, because we have two types of charge carriers. So if you look at this energy band concept here, the movement of electrons, as we discussed, it is in the conduction band. Free electrons in the conduction band, under the action of external electric field, they can move in this direction if you apply electric field in this direction. But if you reverse the electric field direction, they will move in this direction, depending on the action of the direction of electric field. Come on. However, this vacancy or hole in the valence band, as you see, they will also move, but the movement of valence band, the movement of hole or the electrical conduction due to this vacancy will take place within the valence band. It will take place within the valence band. Okay, so because of as I said from the very beginning, the valence, those electrons which are in the chemical bonding, they are in the valence band. So all this motion of shifting of electrons from one chemical bonding to another chemical bonding, they will occur within the valence band. They will occur within the valence band. All right. So free electrical conduction occur in the conduction band. Whole conduction takes place within the valence band, because they are simply the shifting of electron from one chemical bonding to another chemical bonding. Right. Now, uh, let us look into what is called extrinsic semiconductors. So far, what we have discussed is called intrinsic semiconductor. Intrinsic semiconductors means those semiconductors without any impurity or any other foreign element. If it is a silicon crystal, all the atoms constituting the semiconductors are silicon atoms. So silicon, as we know it, it is having a 4 valence electrons. So all these 4 valence electrons, they contribute to chemical bonding with the neighboring 4 valence electrons. And as we just discussed, the only way we are having free electrons and holes is by dislodging one of the electrons in the chemical bonding. So by dislodging, we create free electron as well as a vacancy. So this is called electron hole pair formation. Oh, I'm so disturbing. I'm so disturbed. Oh, hello. Di nenge puma pui lo phone the class ka lag lo to ka class ka lag lo mi run phone mi nge am zia boy na name. Na zo thori lo pot ro chun na ki na tho the ve kan shil don ni oh. Ti kan lo pot ro oh na tho the na shil don ni. Hmm. So now, let us jump to what is called extrinsic semiconductor. So in extrinsic semiconductor, we are inserting external atom, foreign atom. The foreign atom in the sense an atom other than the constituting atoms. So in the silicon crystal, the constituting atom is silicon, but if we insert another element in the silicon crystal, this is called extrinsic or doping. So inserting another atom is called doping. Right. Just a minute. Inserting another atom is called doping. Now, here, in place of this silicon atom here, suppose I insert pentavalent atom. Pentavalent atom like lead here, Pb. Pentavalent atom means 5 valence electrons. Okay, 5 valence electrons. So in place of one silicon atom, if I substitute this silicon atom with pentavalent atom like this lead has 5 valence electrons. One valence electron, they will have a covalent bonding with this silicon. Another valence electron, they have covalent bonding with this valence electron covalent bonding with a neighboring. And the 4th valence electron also will have a covalent bonding with the 4th silicon atom. Okay. And in addition to that, as I said, this is having a 5 valence electron. It has one extra electron, right? So this extra electron, they do not participate in the chemical bonding. So this extra electron is loosely bound. Loosely bound extra electron is loosely bound or attached to this pentavalent atom, because it is not participating in the chemical bonding. So it is very loosely bound or attached to this pentavalent atom. And if you have certain thermal energy above 0 Kelvin, because of the thermal energy, this loosely bound or attached electron to this lead atom, they can easily get detached. And they will become free electron. Easily it will be detached above 0 Kelvin and they will become free electron. So as you say, if you insert one pentavalent atom, it will result in what is known as one free electron. It will contribute to one free electron. So by doping, that is by inserting, by replacing one of the silicon atom with one pentavalent atom like lead here, we are now having one free electron. If you insert 1000 lead atom here, you will get 1000 free electrons. So the number of free electrons created here because of this doping will be depending on the number of foreign element you inserted in that silicon crystal. All right. And another type of extrinsic semiconductor. Okay, by the way, this type of extrinsic semiconductor is called N-type semiconductor. Why do we call it N-type semiconductor? By doping with this pentavalent atom, we are having one negatively charged free electron. So N-type semiconductor, because it already has large quantity of free electrons, negatively charged uh, charge carrier called the free electrons. Right, so it's N-type semiconductor. Now, suppose in place of this silicon crystal, you replace this silicon crystal with a trivalent atom like boron here. Trivalent means three valence electrons only. Okay, okay. So one valence electron, it will contribute to chemical bonding with this. Another valence electron, chemical bonding with a neighboring, another chemical valence electron. But in order to have a chemical bonding with the fourth silicon atom here, this trivalent atom, they do not have any sufficient valence electron. So if they do not have any sufficient valence electron, they create what is known as a vacancy. They create what is known as a vacancy. Okay, so this vacancy or hole in the chemical bonding, as we discuss here, vacancy or hole within the chemical bonding here, they can also contribute to electrical current, which we call it hole current, Okay, so hole is the second charge carrier. A free electron is one of the charge carrier. Hole is another charge carrier. The new concept we introduce in a semiconductor. This is whole concept is not available or is not relevant in the case of a normal conductor. So in this silicon, we have a whole concept because it can contribute to electricity as we just explained here. So uh, by inserting one trivalent atom, we are creating one hole here. If you insert 1000 trivalent atom, you will have 1000 holes which can contribute to electrical current by shifting within the valence band, by shifting or by moving within the valence band. Right. So this type of semiconductor, once it is doped with trivalent atom, is known as p-type semiconductor because hole, it is of a deficiency or vacancy of negative charge, means we can consider it as a positive charge, even though it's actually it's a simply a vacancy. Right. So in usually when you do the doping in extrinsic semiconductors, we are inserting those foreign element, the trivalent atom or the pentavalent atom, in sufficiently large quantity. Therefore, they will result in large contributing amount of free electrons or large amount of holes, and we call we call them as a majority charge carrier. So here in N-type semiconductor, similar to the intrinsic semiconductor we discussed before, because of the thermal energy, some of these electrons may get dislodged and become free electron and result in uh, vacancy or hole. So there is always electron hole pair formation above 0 Kelvin. But in N-type semiconductor, because of the large amount of lead atom or the trivalent atom which is inserted in the silicon crystal, the quantity of electrons, the quantity of free electrons is much, much greater than the quantity of holes in N-type semiconductor. So the number density N represents the number density of free electrons. If H represents the number density of, sorry, if P represents the number density of holes, the number density of electron is much greater than the uh, number density of holes. Therefore, in n-type semiconductor, electrons are known as majority charge carrier. However, holes are known as minority charge carriers. Holes are known as minority charge carrier in n-type semiconductor. Electrons are known as majority charge carriers because the doping or the number of pentavalent atom inserted is usually insufficiently large quantity, and it results in large quantity of free electrons. But at the same time, at room temperature, just like intrinsic semiconductor here, very few amount of electron hole pair formation will occur because of the random thermal energy. Very few amount of electron and hole will also be pair formation will occur, and we will have a very small quantity, relatively very small quantity of holes, relatively very small quantity of holes. Therefore, holes are in minority. And similarly, in a B-type semiconductor here, by inserting large quantity of trivalent atom, we can create large quantity of holes. So if P represents the number density of holes, the amount of electrons, free electrons, that is the number density of free electrons, N, is much lesser than the number density of holes here in P-type semiconductor. So holes are majority charge carrier. Electrons are minority charge carriers in P-type semiconductor. Okay, that's how we classify the charge carriers, which is majority, which is minority. But in the case of in the case of intrinsic semiconductor, without any external doping, without any external foreign element, you cannot have any extra electrons. So electrons and holes are always formed in pair. So in intrinsic semiconductor, number density of electrons is always equal to number density of holes. Okay. In intrinsic semiconductor, number density of electrons is always equal to number density of holes. And the electron hole pair formed because of the thermal energy is usually very less.